So now how do we train this neural network so that it optimally predicts stimuli from neural responses? So first we need to define a loss function that we are optimizing the network to minimize. In this case, we want to minimize the squared error between the prediction and the stimulus. So first we're going to run the neural responses through the network net to get this out. And then we're going to declare our loss function here using this built-in MSE loss function from Pytorch to create a mean squared error loss function. This loss function takes two inputs, which is out, which is the output of the network, and then in this case ORI is the true orientation that the mouse saw on the screen. So once we've defined this loss function, we minimize this loss function using gradient descent. In gradient descent, we compute the gradient of the loss function with respect to each parameter, which in this case is all of our W's and our B's. We then update the parameters by subtracting a learning rate alpha times our gradient with respect to the loss function L. So let's visualize this loss function with respect to a weight W. If the gradient is positive, as it is in this case, at this position, then we want to move in the opposite direction to minimize this loss, which is in the negative direction, which is as defined here. So we accordingly update W in this negative direction, in the opposite direction of the gradient. And so once the iterations of the training are complete, ideally the weight will be at a value that minimizes this cost function. In reality, these cost functions are not convex like the one I showed on the previous slide, and they depend on hundreds of thousands or millions of parameters. There are tricks to help navigate this rocky cost landscape, such as adding momentum or changing the optimizer, but we won't have time to get into that today. There's also another way that you can change the architecture of the network to improve optimization, such as including skip connections. And these skip connections are used in residual networks to allow for the optimization of these really deep networks. So in our case, we're working with a single layer network, a single hidden layer network. So we're going to stick with standard gradient descent in Pytorch, which you can create this optimizer called optim.sgd, or stochastic gradient descent, to do this optimization. And the optimizer object takes as input the parameters, net.parameters, and it takes also as input the learning rate that you want to use. So on each iteration, we're going to run the training data through our network, net, and compute the loss function. And then once we have the loss function, we're going to clear our gradients, and we're going to compute our gradients using this loss.backward method. And so this loss.backward method is also known as automatic differentiation, and this is an incredibly powerful tool. You can use this backward step for any model and any loss function that you can define in Pytorch, not just deep networks. So I highly recommend using it when you're fitting complex models rather than computing gradients using pen and paper. It's much less error prone to do it this way, and it will save you a lot of time. So finally, once you've computed the gradients using this automatic differentiation that's built into Pytorch, we update the parameters using this step function, this step method of the optimizer, and then we repeat this method or this loop for many iterations.